Well, good morning, everybody. Um, Once again, it is freezing here at headquarters. It's just the way it goes out here. Cold at night and hot during the day. Are there questions or issues that you want to bring up before we jump back in? Well, cool. So we're gonna get all like mathy today. Um, not not so much like a math class. Our point of view is not going to be theoretical. It's going to be uh, sort of using mathematics from an engineering standpoint as a way to figure out how to write a bunch of code. Is this where the linear algebra requirement comes in? Well, the linear algebra thing, it's partly tradition that it's a prereq for a graphics course. And it's partly that um, it seems to help people to have had some other exposure in a different kind of course to the world of vectors and matrices in 3D coordinates. But I do not plan to prove any of those highfalutin linear algebra theorems, such as you might see in a course. And for another thing, everything we do is in 3 dimensions. You know, we don't really care about n-dimensional space. On the other hand, the way that we think about 3 dimensional space might be slightly different than what you find in a math book. And that's going to be one of the first challenges, you know, is that your minds have been corrupted from too many math books. I'll show you what I'm talking about with a little example. Um, let's say this is the real world. This is a portion of the real world, perhaps Ames, Iowa. And over here is my house. And the location of my house is described with coordinates. Now, the question is, from the point of view of somebody over here at the clock tower on Welch Avenue, the way the world works is important direction. First, somebody needs to mute or try chatting because you're just making incomprehensible sounds. That's Akalesh, are you asking a question? Yeah, right. Turn off your vacuum cleaner. All right. So we'll suppose that we have a vector pointing that direction. Or one way to think of it is this represents the orientation of a coordinate system with a scale like this, right? And maybe the scale is measured in miles or units of 100 yards or whatever. And then the other direction is you have to get over to West Ames. Well, again, you've got another scale going that way. And so according to that scale, the coordinates of my house might be something like, you know, 1, 2, 3 in the positive direction and units of 5 in the negative direction. And one way to think about what those coordinates mean is that if I'm at the clock tower, the coordinates are giving me instructions on how to get to Steve's house, which is you follow direction A for 3 units and you follow direction B for -5 units. But that's not really how I think of the location of my house. The way I think of the location of my house is over here, you have the intersection of Main and Duff. And it's measured in terms of streets and avenues, right? So the units go something like this. And My house is, by the way, is 309 11th Street, as is known to the post office. But in terms of this coordinate system, I go 3.2 units in the first direction, followed by 11 units in the Duff direction. And that's how I think of the coordinates of my house. Now, notice that whether I'm standing at the corner of Main and Duff, or whether I'm standing at the corner of Welch and Chamberlain, my house doesn't move, right? But relative to this coordinate system, it has one pair of coordinates. Relative to this coordinate system, it has a different pair of coordinates. And so what that tells us is knowing the coordinates doesn't tell you enough. You also have to know what's the coordinate system, or in other words, what is the frame of reference for describing a point in space. Yeah, so anyway, this is, believe it or not, one of the most important insights of the entire next 2 weeks is the fact that knowing the coordinates of something doesn't tell you where it is. You also have to know the frame of reference. And where I'm coming from here, I just want to kind of briefly remind you of a picture we sketched on the first day. What's going to be happening to us over and over again is we're going to start with a model. We're going to transform the coordinates of that model so that they appear relative to a scene or a world in which we want to place it. From there, we're going to transform the coordinates. So we're describing the model relative to a camera or an eye. And then from there, we're going to transform them again into this sort of ridiculous, arbitrary notion of the clipping volume or clip space. And what's going on here is that we're not actually ever moving the points, the vertices or the points that make up the model. We are simply creating new coordinates for them so that we know where they are relative to the world. And then we create new coordinates so we see where they are relative to the eye. And then we create new coordinates so we see how they fall relative to the clipping volume. And so this is one of the hard things to get used to, is that we have to sort of separate the notion of what is a point, what is a vector, and what are the coordinates of the point, what are the coordinates of the vector. And I want to do a couple of little exercises today to get through this idea of what does it really mean to say that I have coordinates for a point or coordinates for a vector. Okay, so that's sort of the warm-up. Where to begin? Before I forget, let me, I forget I want to mention which sections are relevant, but I have to look it up. Sorry. 212231. Okay, so I wanted to mention for your benefit that a lot of the notation that I will be using is adapted from this book by Stephen Gortler, and there's really just a few pages in these sections of the book 2.1, 2.2, and 3.1, but it's a nice, very, very concise description of kind of the basic ingredients that make up the world in graphics. And this is, again, if you look on our resources page, you can read this book for free through the ISU library. Just do a search for its title once you're on the library page. So think of where I am standing as something we are going to call the real world, and the whiteboard is just an arbitrary plane within the real world. the real world has 3 dimensions, and you can think of the third dimension as sort of going out towards the camera. But I don't draw very much in that third dimension because it's really hard to draw. Okay, so in the real world, we have things that we call points. And we'll represent those with a twiddle over the top. So you have a point P and a point Q, let's say. And think of these as physical locations in the real world. A point is not a pair of numbers or a triple of numbers. It doesn't become a pair of numbers or a triple of numbers until you have settled on where's the origin of the coordinate system and which direction do the axes go. And this is completely misleading if you're used to doing math out of math books, because in a math book, there's only ever one coordinate system, and it's always in the same place and oriented the same way on the page. So you never have to think about this. So you have this bad habit from physics and math books of thinking that, if I draw a vector like this, well, that must be the vector 2, 1, right? Because it goes over 2 units and up 1 unit. But this is not the case. So don't do it. All right. So to keep going, we have points labeled with a twiddle, and once you have 2 points to look at, you could say, I wonder, how do I get from point P, or say from point Q to point P? And the directions, the set of instructions to get from point Q to point P would involve, well, you need a direction and you need to know how far, right? So we have a direction and a distance, and we think of that as a vector. Call it V. I notice it has a little arrow over the top in our notation. So what can we do with points and vectors? So a vector is a direction and a length, but it doesn't really have a location, right? Because it's just a direction and a length. So this is all V. We can draw it wherever we want, and it has exactly the same meaning. Points, you can't move them around. A point is a specific location in space. So that's kind of where it all comes from. So you can deduce from this that the difference between 2 points is a vector. In other words, the way you could describe this is to say V is the difference P minus Q. It's how I get from Q to P. Okay, so that'll be handy to be aware of. You can take the difference between 2 points, you get a vector. And likewise, you could rearrange that equation a slightly different way and say a point plus a vector is a point. That is, you could say Q plus V gives you a new point. And that's not too surprising based on the real world, right? If you're in one place and I tell you go two paces forward, you're in another place. Now, what about adding vectors? Can you do that? And the answer is sure. If we take 2 vectors, this is the part you've seen before. Of the sum or difference of vectors is a vector. And one way to think of it is that if I take, let's say, a vector u, and I take another vector v, and I want to know what is u plus v, you can sort of think about it as a head to tail or a parallelogram rule. Remember, we can draw them wherever we want, so it's convenient to stick the tail of v to the head of u, and And that gives us this vector. And the way to think about it is, well, this is a set of directions to get from here to here. This is a set of directions that get from here to here. So if I do both of them, I go here and then I go here. Well, I could have just taken the straight line. And so that's the resultant, or the sum of the two vectors. Now, what about the difference? The easiest way to think about the difference of vectors is to think about scaling first. So in our world, we can scale vectors. For example, if this is u, then 2u would be like you do u and then you do it again, right? And you can also have something like minus 1.7u, which would be, well, you take u and go the other direction and scale it, something like that. So that would be u, and this would be 0.7u. And it's minus because you're going the opposite direction. None of this is too surprising, I hope. And so the vector difference, u minus v, is just u added to the vector minus v, is the easiest way to think about it. So it's not really a new operation at all. Now, what if I take a vector and I subtract it from itself? And that leads to something that is perhaps an anomaly in the world of vectors. It's the zero vector. And with the zero vector, easy to obtain just by taking, say, u minus u. It has length 0 and direction is undefined. All right, so when we talk about the length of a vector, again, think of this as a physical measurement of space. So the length of v is denoted this 2 vertical bar notation. We're going to be interested many times in using vectors of length 1 because they're convenient and they're easy to scale. Right? In other words, if I have a vector of length 1 and I scale it by 5, how long is it? Well, it's length 5. So we like them for that reason, and other reasons too. So a vector of length 1 is a unit vector, and is said to be normalized. So normalizing a non-zero vector u is you just divide it by its length. Or what I should say is you scale it by 1 over its length. So this always has length 1. Right, so you can make any vector into a unit vector just by scaling, multiplying by 1 over its length, as long as it's not the zero vector. Right, so normalizing vectors is something we need to do frequently. So what happens to us a lot is that we end up with a set of vectors, and we look at what happens if you scale them in various ways and then add the scaled pieces together. So if you're given a set of vectors, let's say Now let's take three of them, U1, U2, two's enough. Maybe there could be more. Any sum of scaled instances such as A times U1 plus B times U2 plus C times U3 is called a linear combination. So it's nothing fancy. You just scale and add a bunch of vectors and you get a linear combination of U1, U2, and U3. Right? And okay, so that'll be a useful piece of terminology to keep stuck in our heads, I guess. Having figured out, well, we have operations of addition and scaling on vectors. We have a notion of a zero vector. We have a concept of linear combination. You get to this idea of a vector space, which is what you tend to think about a lot in a linear algebra course. So a vector space, and I'm going to say a 3D. Let's stick to 3D. A 3D vector space is just a collection of all possible 3D vectors with these operations. Is probably the best way to think of it. All 3D vectors with the above operations. In other words, addition and scaling. Hey, this is not where we're going to live. We are going to live in what's called an affine space, which is a little bit richer because it includes points. So a 3D affine space includes 3D vectors and points, along with the two operations we mentioned earlier, that you can take the difference between 2 points and get a vector. You can add a vector to a point and get a point. There's no such thing as adding 2 points. That concept doesn't make any sense, so that operation doesn't exist. But the operations we mentioned that actually do kind of make intuitive sense, that forms a 3D affine space. All right, and we will spend most of our time in affine space because we have to deal with vertices or points. So this leads us to an idea. So I'm going to do it first with vector space. Yeah, so that's a good question. Vectors can be used to describe points once you have chosen an origin. That is exactly 100% correct. But the concept of a vector space, if you study it in a linear algebra class, there is no concept of point. As soon as you introduce an origin, right, as soon as you have 1 point, then because of the vector addition property, you have simultaneously defined all points, so they are now part of your space. I hope that answered the question. So an affine point is not different than a point that you're accustomed to. It's just that in a pure linear algebra sense, a vector space does not contain any points. Yeah, I hear you. let's see. So here's what I wanted to look at. That's a good way to look at it. So an affine space can be thought of as a vector space with an origin. Let's keep going. What I wanted to observe is, let's suppose you've got two vectors, say u and v. And let's imagine this is, again, three-dimensional space, but I'm going to ignore the third dimension for now. But it's sort of there implicitly, but we'll ignore it. So what the question I'm kind of wondering about is, what if I take some arbitrary vector, let's call it W, and the question is there, I'll write that down, can I find numbers A and B such that W is A times U plus B times V? In other words, can I find a linear combination of U and V that will add up to give me W? And let's try it, right? We know we have to, we add vectors using this sort of parallelogram rule. So what if I took the tail of W here, and I just draw a line that's parallel to U, and I take the tail of W and I draw a line that's parallel to V. And we could draw another parallel line here, another parallel line there. And we could say, what is the vector W? Well, it's a set of instructions for getting from its tail to its head. Now, is there a way that I can get there only using these two directions? And the answer is sure. We could do it like this. We could go V, and then V, and then like 0.2V. So we'll call this 2.2V. And then we could follow U, except we have to go the opposite direction. So if we go down here, that is going to be about, say, minus 0.6 U. But notice if I take 2.2V and I add minus 0.6 U, I'm going to get the vector W. Right, so we would say the answer to this question is yes. The W, in fact, is equal to minus 0.6 U plus 2.2 V. Now, if I take some other vector in my space, X or something, do you think it's possible for me to find a linear combination of U and V that gives me X? And hopefully the answer is yes, that I could do this trick for any vector that you want to come up with. And I'll always be able to do it. And there's a I guess an idea buried here, which is that you could say that U and V form what's called a basis for the two-dimensional plane that we are working in. And that's kind of an idea that we need to have, is that basis or a vector space is a set B of vectors. And just to keep the notation simpler, let's say it's three-dimensional. The set B of vectors B, let's say B1, B2, B3, such that every vector is a linear combination of B1, B2, and B3. And the key points here are not very hard to see. The reason it works with my first two vectors here, U and V, is that they're not pointing the same direction. If they were pointing the same direction, this would be impossible to do because I could only take linear combinations that would give me vectors in the same direction. And the intuition still works in 3 dimensions. You need 3 vectors that are not collinear and that are not all in the same plane, and then you will be guaranteed to have a basis, which we will not prove. Yeah, okay, yeah. So they can't be the same, and they can't even be in the same direction. So that's the idea behind this bit of intuition. 3 vectors must be non-collinear. They can't all be along this. They can't be along the same line and not in the same plane. So no, we're not proving anything. Yeah, the thing is, if you're trying to do this for arbitrary dimensions, you have to engage in a lot of care to define the notion of independence that enables you to define a basis for n dimensions. And I remember the first time I took linear algebra, it was really exciting getting to the part of the course where we proved that 3-dimensional space is actually 3-dimensional, according to the careful definition of dimension. And we're going to take a much more relaxed point of view about this because we are only interested in working in 3 dimensions. And there's a very simple intuition that we have in 3-dimensional space, which is this is what it means for 3 vectors to be independent. No 2 of them are in the same line, and they're not all 3 in the same plane. And then you have this property that you could get anywhere in the whole space just by taking linear combinations of those 3. And I've illustrated that in a 2-dimensional segment, but it's easy to kind of extrapolate from that to say, well, if I had a 3rd vector, then I could get anything in 3 dimensions. Okay, so that's the idea of a basis. So coming back to these 2 numbers that we came up with for scaling U and V to get W, it's reasonable to say, let me write it down, make it even more reasonable. So if my basis B consists of these vectors U and V, and a 3rd one that we don't care about because we're not looking at the 3rd dimension, then we would say that I'm going to draw it like this: 0.6, minus 0.6, 2.2, and 0. What I'm trying to say is that you can think of these numbers as being coordinates. But in order to have coordinates, you need a frame of reference in which to use them. And in this case, for just describing vectors, our frame of reference is a basis. This is a coordinate vector. Is this visible? I can't tell.
We can see it.
Can you see if I write down here?
Yes, I can.
Okay. This is a coordinate vector for W with I need, I'll continue up here. With respect to, which mathematicians like to abbreviate WRT, the basis B. Right, so I've drawn this very deliberately as a column matrix, and I want to extend this idea of coordinates and bases a little bit. But first, remember, we're not really that interested in vector spaces in that pure sense. We are interested in affine space. And so let's go ahead and define what we mean there. A coordinate system or frame for an affine space is a basis plus an origin, which is a point. And when you talk about linear combinations in an affine space, you do exactly what Enzo was saying in the chat, which is you get a vector by taking a linear combination of the basis vectors, and then you just add it to the origin. So if you have a situation like this, where you've got an origin, let's say O, and I've got a vector, which I could think of as taking me from the origin to somewhere else, which let's call that point P. Notice that you can write P equals, I'm kind of assuming I've got the same basis, point minus 0.6 times U plus 2.2 V plus 0 times the whatever vector plus the origin. And by adding that vector to the origin, then you've specified a point in space, a specific location in our affine space. So this notion of linear combination of vectors, you can actually extend it to the notion of adding on a point. And so we could say minus 0.6, 2.201, the coordinate vector of P with respect to the frame consisting of my original basis, script B, and the origin O. What I want to do in a second is introduce some better notation for this, but we will, in general, think of the coordinates of a point as a column vector with a 1 in that fourth component. And the reasons for this will become clear, I think, pretty soon. How's everybody doing? We should take deep breaths and do some jumping jacks. Get woken up again, so we don't overdose on math. So yeah, because it's going to get worse before it gets better, I think. Okay. So what we need to do to sort of streamline our ability to talk about this stuff, and most importantly, to streamline our ability to write code about this stuff, is we need to quickly review matrices. I'm gonna let me do something here. Polling. Can I do this? add new question. I want to, just a second, open poll questions. Give me 1 second. I'm looking for something on my, I'm misplaced SMCounts. ISU 227 polls. Okay, so okay, I'm opening a poll, and the question is, have you done matrix multiplication before? All right, we're looking pretty good. All right. I mean, it's an assumption that I kind of have to make because otherwise we could get really bogged down. If you are one of the people that is not sure, I'm gonna review it real quick right now, and you'll find it's very easy to get used to. It's really just a simple nested loop. And let me return to the question there. Okay, this is getting there. 10 people not answering. You fell asleep? You don't even like turtles? Oh, yeah, to answer your question, Enzo, you're right. Yes, that's exactly right. Affine space is a basis plus an origin. And once you introduce that origin point, then you can describe all points and work with them. All right, let me close this poll. I think we're getting pretty positive responses. Most people have done matrix multiplication before, and no, we're not going to do quaternions today. Dream on. No, we just want to do this, matrix multiplication. So if you take something like this, 1, 2, 3, 4, 5, 6. So this is a 2 by 3 matrix. It's always rows, columns, just like Java two-dimensional arrays. And let me take another two-dimensional array here. How about 0, 1, 2, 1, 0, minus 1, 2, 0, 3. What does it mean to multiply these together? And we're basically just going to take the, we're going to write a nested loop that will take this row and this column and generate an entry over here. Right? So, and the rule is this times this, this times this, this times this, added together. So 1 times 0 is 0 plus 2 times 1 is 2, that makes 2, plus 3 times 2 is 6, 2 and 6 is 8. So we would get an 8 in that entry. And you can keep on going like that. You had a different color. You could say, well, I want to take that row and that column, and that's going to give me that entry. So 1 times 1 is 1, plus 0 would give me an entry of 1. And we can keep going like that. 2 plus minus 2 plus 9 would be 9. And then second row, first column, 4 times 0 is 0, plus 5 plus 12, 17. Second row, second column. 4 and 0 and 0 is 4. 8 minus 5 is 3 plus 18 is 21. And so that's how the entries in the result are generated. Notice this is 3 times 3, or a 3-row, 3-column, and the result is going to be 2 rows, 3 columns. And the idea is these, in order for that whole operation to make sense, these have to be the same. And that purple, yeah. And that you start out with 2 rows, you end up with 2 rows. You start out here with 3 columns, you end up with 3 columns. So that's how it works. Anyway, there is a huge wealth of resources online. I can recommend 1 or 2 of them if I can remember to look it up after class, but if you need to review this a little bit. But it's a really simple operation. I mean, once you've seen it once, it's hard to get it wrong. You can deduce a couple of things from this, which is that if I were to label this matrix A, B, and C, we're saying A times B equals C. On the other hand, B times A is nonsense. We would say that these are incompatible. And so the thing you can deduce immediately is that unlike multiplication of numbers, this operation is not commutative. All right, so that's a general thing to be aware of. A couple of other things that are useful. If I could just take the liberty of erasing some of this. What if I took a matrix that had 1s on the diagonal and 0s everywhere else? Like that. So it has to be square. In other words, same number of rows and columns. And you should do this exercise once in your life. If you haven't, just try this and see what happens. I get 1 times 1 plus 0 plus 0. It's 1. I get 1 times 0 plus 2 plus 0 is 2. I get 0 plus 0 plus 3. And you can sort of see what's about to happen. I get 4 plus 0 plus 0. I get 0 plus 5 plus 0. I get 0 plus 0 plus 6. And I have exactly the same matrix I started with. So a matrix, square matrix, I should say, with 1s on diagonal and 0s elsewhere is an identity matrix, typically called I, and it's the case that A times I is always equal to I times A, which is equal to, I shouldn't say this, A times I equals A, and I times A equals A, assuming they're compatible. I couldn't take this identity and put it on the left of A. I could, however, take a 2 by 2 identity and put it on the left of A. In other words, I could take 1, 0, 0, 1 times 1, 2, 3, 4, 5, 6, and you can see what would happen, right? Then I would get 1 times 1 plus 0, 1 times 2 plus 0, 1 times 3 plus 0, and so on. So this equation always works, but the identity has to be compatible with the size of the matrix to multiply it at all. There is also a notion of, well, let's see. Let me mention one other thing about multiplication. This is important. Matrix multiplication is associative. I'm not going to prove this. It's an easy proof, but it's just tedious as all get out to work out the details. But basically, A times B times C is the same as A times B times C. As long as you don't change the order and as long as they're all compatible, that'll always work. And that'll be important for us. All right. Let's see. I guess while we're on this, there is also such a thing as matrix addition, which is a little bit more intuitive. And all I want to say is that it's component-wise. So that says the matrices must be the same size. Unlike multiplication, where they can be different sizes as long as they're compatible, meaning the rows and columns match up right. Count for the left and the right sides. For matrix addition, you can only add matrices that are the same size. So if you have something like 1, 2, 3, 4, you can add it to something like 5, 6, 7, 8. And the result is kind of what you'd expect. You add the 1 and the 5 to get 6. You add the 2 and the 6 to get 8. You add the 3 and the 7 to get 10. You add the 4 and the 8 to get 12. And that would be my matrix sum. You can also, there's also an operation of multiplying a matrix by a number. You could say something like 2 times the matrix 1, 2, 3, 4 would be the matrix. You just double everything, right? 2, 4, 6, 8. Again, fairly intuitive, I think, but we'll kind of take that for granted as well. So far so good, I guess. Now we can define coordinate vectors a little bit more carefully and improve the. All right, I thought I lost my marker, but maybe that's it. And improve the notation a little bit now that we've got this notion of matrix multiplication and addition. So here's what we'll do. So given a frame, with basis vectors B1, B2, and B3 with origin O, we write it as a row vector or a row matrix. So B1, B2, B3, O, like that. Okay, so that's what we're going to call a frame or a coordinate system, is this row matrix consisting of your basis vectors followed by your origin. Now, a coordinate vector a coordinate vector, say C underscore, using Ortler's notation, for a point P consisting of, let's say, C1, B1 plus C2, B2 plus C3, B3 plus, remember, we're going to take a vector and add it onto the origin to reach a point. Officially, a coordinate vector for that point is C equals, and it's a column matrix consisting of C1, C2, C3, and 1. And now I'm going to hopefully make it clear why this particular notation is chosen. So this is a coordinate vector. These are just numbers. This is something quite a bit more abstract. These are, physical vectors and a point. But we can still multiply them together using the notation of matrix multiplication and get something like frame times coordinate vector gives you the point. And if you think about what happens when I multiply this matrix and this matrix, are they compatible? Yes, this is a 1 by 4 matrix. This is a 4 by 1 matrix. So this times this plus this times this plus this times this plus this times this gives me exactly the description of the point P. So that's kind of the way that we're going to work with these things, is that you've got a coordinate vector that you believe has meaning with respect to some frame, and to decipher the meaning of that coordinate vector, you simply multiply it by the frame. Now, what about just vectors? I've said that our affine space contains points, but it also contains vectors. And that's easy too. Coordinate vector C, or a vector, let's say V, consisting of C1, B1 plus C2, B2 plus C3, B3. Right, so this is a pure vector. It's not being added to the origin. It's going to be 3 numbers representing those coefficients on the vectors, followed by a 0. And again, you take your coordinate vector, you multiply it on the left by the frame, and what you get is exactly that expression where you think of the 0 as canceling out the presence of the origin. So this turns out to be a really convenient notation for many, many things that we have to do. Is to use this matrix multiplication to represent frames and vectors and points. And this notation that we're choosing for coordinate vectors is very convenient in a lot of ways. So for example, suppose I have 2 vectors. I'd say with coordinates say C1, C2, C3, 0, and D1, D2, D3, 0. And you add them together, what do you get? Well, C1 plus D1, C2 plus D2, C3 plus D3, 0. And notice that this is still a coordinate vector for a vector. All right, so that is still a vector. And likewise, if you take vector for a point, C1, C2, C3, 1, and you add a vector, D1, D2, D3, 0, lo and behold, you get something that represents a point. What if I take the difference between 2 points using this coordinate vector notation? And this is not too hard either. The difference between 2 points, in other words, if I take something, 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 1, and something, 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 1, it's going to be something, 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 0. It's a vector. Oh, sorry, 6 feet. So am I going off this direction? No, this is okay. This is okay. Am I losing you at the bottom or on the left? Because, oh yeah, here's where I messed up. Oh yeah, I suppose. All right, let's see. So that's a good question. It says, the question is, what happens if you have an origin that's not equal to 1? The origin is not 1. Remember, when you look at a frame, it consists of 3 basis vectors. And a point. So the point, the origin is a physical thing in 3-dimensional space. The 1 is a notational trick that enables this notation using a column matrix as a representation of the coordinates. Think of it as a notational trick that enables this to work out nicely. Now, yeah, one of the things we're going to discover is that the fourth component in our coordinate vectors is really a lot more significant than that, but it's not an idea that I want to get into until we need it. We'll discover there are several levels of depth in this, but this way of representing points and vectors using these size 4, right? These 4x1 column matrices. These are called homogeneous coordinates. And this is, as I mentioned, we're recycling a number of ideas out of 19th century mathematics, and homogeneous coordinates is one of them. And it just turns out to be precisely the thing we want to efficiently do calculations in graphics that can then be hardware accelerated on our GPU. And so the convenience of this notation just to represent the coordinates for points and vectors using these column matrices, that's sort of the tip of the iceberg. It gets much more interesting once we get a little farther into it, as I think you will see. So this is just sort of the first layer of why do we use these apparently 4-dimensional things to represent stuff in 3-dimensional space. And that's where the idea gets a little bit deeper. But right now, think of it as kind of a notational or a computational trick to make the notation work really well to represent points and vectors relative to frames. Ah. Ba, ba, ba. Yeah. Are there other questions? Is there anything bugging you about this? Okay, so I think, okay, so hopefully that suffices as an introduction to this set of concepts. And really the most important takeaway is that a coordinate vector is just 4 numbers. Right, and it's going to have the form A, B, C, 0, or A, B, C, 1, depending on whether it's coordinates for a vector or coordinates to a point. Let me come back to that question. So we want to distinguish very, very carefully between a set of coordinates for a point versus an actual point, and a set of coordinates for a vector versus an actual vector, right? So if I take a coordinate vector C, that's just a bunch of numbers that are by themselves meaningless, right? But if I take and I multiply on the left by a frame, this is really a vector. So coordinates only have meaning with respect to a frame, and we always have to keep the frame in the back of our minds when we're talking about coordinates. Because what's going to happen is that the frame is going to be transformed, because we're going to want coordinates with respect to different frames of reference as we move through the graphics pipeline. So that's going to turn out to be like this D. We can take F times D is really a point, just to fill that in. So that's a key idea, and we just we will find that when we are writing code, we are always going to be working with coordinates, because these are the numbers that we can actually represent in the CPU. The frame is a mathematical abstraction. This is our description of some entities in the real world, vectors and points that have a geometric reality right here. And we can't, the frame never finds its way into actual code, but it has to remain in our minds for us to understand what we're coding, is I guess one way to look at it. So this is a good place to begin. Let me see if I can answer that question. So you could describe an object relative to a point on it and then adjust the coordinate vector for that point to adjust the position. I think there are going to be two things happening. So one is we will actually need to make things move. So we will take, say, some vertices, some points, and we will apply transformations, and that will give us new coordinates that are actually having the effect of moving an object through space, right? So that's part of it. The other thing we'll do is we'll say, well, I've got some coordinates here, maybe representing something, and they're described relative to, say, a coordinate system here, but I have a different coordinate system over here, and I want to know, if I'm here, what are the coordinates of those points? And this is sort of more the idea of Steve's house, that my house isn't actually changing its position, but the description of where it is relative to the clock tower is different than the description of where it is relative to Main and Duff. So we're going to do both kinds of things, and there's a relationship between these two operations. we're going to transform coordinates to move a thing, we're also going to transform coordinates to move the frame. And it turns out that these are closely related. And I don't think we're prepared to get into that sort of transformation just yet, but we will next time. I think, do I have time to do this? One thing that was on my list of things to mention today that I suppose I should is the dot product. So a dot product is a vector operation that results in a number. And the mental picture is if I have two vectors, let's say u and v, again, if I stick their tails together, I can look at them in the physical world, and there's some angle that they form, possibly 0 if they're pointed the same direction, or 180 degrees. Anyway, so there's the angle between them. And the definition of the dot product, u dot v, is it's the length of u times the length of v times the cosine of the angle between them. Or you would say u dot v is just the cosine of the angle if u and v are normalized. Which means they already have length 1, so this factor doesn't do anything. When you first see the dot product in physics and math books, it's often defined in terms of the coordinates, and we can't do that. I'm losing my black marker. What happened to the? I swear somebody is coming in and stealing my markers. Oh, there it is. So in some cases, I guess I should say, we can calculate this dot product. In other words, we can calculate the angle from the coordinates, as you have done in a math book. But it doesn't work. It only works, in some cases, it only works if the basis is orthonormal. And I don't think we want to get into the definition of that quite yet, but we'll come down to it. But I did want to make this connection that the angle between vectors is a meaningful geometric concept, right? And the dot product is a way of describing semi-directly the angle between vectors. You don't get the angle, you get the cosine of the angle, which for our purposes is actually a lot more useful in most cases than the angle. And when we start doing some more stuff in our shaders, you'll see why. The cosine is a useful quantity to have. But we need to make sure before we do this calculation in terms of the coordinates that we're actually working with a basis for which that makes sense. And I think I'll have to come back to that notion of orthonormal basis, I guess, when it comes up. But for now, take a few minutes and read those few sections. It's only about 6 pages of reading in the book by Gortler, which will help reinforce, I think, the notation and maybe some of the ideas. He does a nice job in the first 5 chapters of that book to sort of lay the mathematical foundation, I think, in a way that's very concise, which most textbook authors are unable to do. Anyway, let's stop there. Any last minute questions? Lecture recordings from last week be posted. Didn't I do it already?
All
right.
Tuesday is up.
Which one?
I think just Tuesday is up.
Okay, I'll check on that. I thought I had done it, but clearly not. Okay, final announcement, in case you had not seen it on Canvas, is I did post a homework assignment. Because I know you need something fun to do. Anyway, that'll be due in a week. So take a look at that soon. I know there are going to be questions. Yeah, yay homework. Anyway, also, I should have put this at the announcements at the beginning. If you look at the syllabus, both me and Gia have posted office hours with links to a Zoom room where we'll be available for further conversation. So office hours, homework, reading, be kind to each other, stay safe. All right, see you all on Thursday.